Hello and welcome to Slow Orbit, the channel where we embark on journeys through the cosmos, exploring the wonders of the universe at a pace that's as relaxing as it is enlightening. If you enjoy unraveling the mysteries of space, don't forget to like and subscribe so you never miss an adventure. And while you're here, let us know where you're watching or listening from, whether you're in a cozy corner of your home or perhaps even gazing up at the stars yourself. It's always fascinating to hear where our cosmic explorations find you. Today, we'll be diving into something truly extraordinary: gravitational waves. These invisible ripples in space-time are not just a theoretical curiosity. They are real, measurable, and were first detected only a few short years ago. You might be sitting on Earth, but what if I told you that the very fabric of space-time, the foundation of our reality, is being disturbed by the violent collisions of distant black holes and neutron stars? That's what we'll be exploring today. How these cosmic events are felt here on Earth as tiny, fleeting waves, altering our perception of the universe in ways we never thought possible. So sit back, relax, and prepare to journey through space-time itself. Let's uncover the strange and mesmerizing science of gravitational waves. Gravitational waves are an incredibly fascinating concept. Ripples in the fabric of space-time itself, generated by the most intense and violent events in the universe. Imagine a massive object, like a black hole or a neutron star, accelerating or colliding with another. These cosmic events send out waves through space-time, much like ripples spreading across the surface of a pond when a stone is thrown in. The key difference, of course, is that these waves are not seen or heard in the usual sense. They are invisible, undetectable to our eyes or ears, but they can be measured with incredible precision. The discovery of these waves has opened up a new chapter in our understanding of the universe and the very nature of space-time itself. Now, let's take a step back and think about why gravitational waves matter so much. In a very real sense, they represent the meeting point between the most fundamental ideas in physics, Einstein's theory of general relativity and the strange world of quantum mechanics. These waves allow us to observe cosmic events that would otherwise be impossible to see. They bring us closer to understanding the inner workings of black holes, neutron stars, and other extreme phenomena. But what makes them so special? Gravitational waves are not just a consequence of massive objects, they are a fundamental aspect of the structure of space-time. At the heart of this is the genius of Albert Einstein's general theory of relativity. When Einstein first formulated his theory back in 1905, he revolutionized our understanding of gravity. Instead of thinking of gravity as a force between objects, as Isaac Newton had described centuries earlier, Einstein showed that gravity is actually a curvature of space-time. This means that massive objects, like the Earth, the Sun, or a black hole, actually warp the space around them. The more massive the object, the greater the distortion in the space-time fabric. And just like when you stretch a rubber sheet and create ripples, when massive objects move or collide, they send out ripples through space-time. These ripples are what we call gravitational waves. The significance of gravitational waves wasn't fully appreciated at first, even by Einstein himself. While he predicted them in his general theory of relativity, he wasn't certain that they would ever be observable. After all, these waves are incredibly faint. The amount of stretching and compressing that occurs is minuscule, even when massive events like the collision of black holes occur. To put this in perspective, imagine a detector on Earth trying to measure the stretching of space-time caused by two black holes colliding billions of light-years away. The change in distance would be less than 1,000th of the width of a proton. That's how small these changes are, so small that they were thought to be undetectable. But that didn't stop scientists from trying. Theoretical work on gravitational waves began long before the first successful detection. One of the important names to remember is Carl Schwarzschild, a German physicist who solved Einstein's equations for the gravitational field around a point mass, before Einstein's formal formulation of the theory was fully fleshed out. Schwarzschild's solution, which led to the concept of the Schwarzschild radius, the size of a black hole, was crucial for understanding the behavior of objects like black holes, which are key sources of gravitational waves. Even before Einstein fully grasped the implications of his theory, Schwarzschild had already worked out many of the details that would help pave the way for later discoveries. Now, when we talk about gravitational waves today, it's important to recognize that we're standing on the shoulders of many brilliant minds. Scientists like Kip Thorne, Rainer Weiss, and Barry Barish. These physicists and their colleagues were the driving forces behind the creation of LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is one of the most sophisticated detectors ever built, and it is designed to measure the incredibly faint gravitational waves passing through Earth. Thanks to LIGO, in 2015 we witnessed the first direct detection of gravitational waves from the collision of two black holes. That moment was a historic milestone, as it proved Einstein's century-old prediction and opened a new window into the universe. But what makes this so mind-blowing is that these waves aren't just a theoretical curiosity. They are a direct way of observing the universe's most extreme events. Black hole mergers, for instance, release energy in the form of gravitational waves. By studying these waves, scientists can gather information about these events that would otherwise be impossible to obtain through traditional telescopes. It's like hearing a song that comes from deep within a cave, where you can't see anything but can make out the details of the music itself. But the story doesn't end with the first detection. Gravitational wave astronomy has become an entirely new branch of science, one that connects us to some of the most bizarre and mysterious phenomena in the universe. And this is where the relationship between classical mechanics and quantum mechanics comes into play. While general relativity describes the behavior of large objects such as planets, stars, and galaxies, quantum mechanics governs the behavior of the very small, particles, atoms, and the strange world of subatomic physics. Gravitational waves live in this intriguing intersection between the two. The paradox here is that general relativity, which has proven itself over and over again on cosmic scales, is fundamentally incompatible with the quantum world. Gravitational waves provide a unique opportunity to study the dynamics of space-time on the larger scales, where quantum effects might come into play, and where the mysteries of the universe's most extreme objects, like black holes, still hide secrets. The future of gravitational wave astronomy might one day unlock the deepest questions in physics, including how gravity works at the quantum level, and whether the universe itself is made up of more dimensions than we can see. By studying gravitational waves, we're not just looking at the aftermath of cosmic events. We're probing the very structure of space-time. These waves allow us to observe the universe in a way that was previously unimaginable, offering a new perspective on how the cosmos operates at its most extreme. And as we continue to explore the potential of gravitational waves, we move toward a more profound understanding of the universe. Could gravitational waves provide evidence for quantum gravity, or even a unified theory of physics? How will the study of these ripples help us answer the question of where the universe came from and where it's going? In the coming chapters, we will explore these questions, drawing connections between gravitational wave astronomy and other fields of physics, like quantum mechanics and string theory, where the answers might ultimately lie. Gravitational waves are more than just a remarkable scientific discovery. They are a glimpse into a universe far more strange and interconnected than we ever imagined. They are the key to unlocking secrets that could reshape our entire understanding of the cosmos. To truly understand gravitational waves, we need to dive into the heart of Einstein's general theory of relativity, a theory that redefined the way we think about gravity. But as with any great discovery, it didn't come from a vacuum. The seeds of relativity were sown by many scientists who came before and during Einstein's time, and their work laid the foundation for what we now know as the science of space-time. Before Einstein even considered general relativity, the notion of space itself was a fairly straightforward idea. It was viewed as a rigid, unchanging backdrop, much like an invisible stage on which all the drama of the universe unfolded. But Einstein shattered this view. He suggested that space was far more dynamic, far more malleable than anyone had imagined. In fact, according to Einstein, space and time are not independent of each other. They are woven together into a single four-dimensional entity known as space-time. The idea that space-time itself could be curved by massive objects was, of course, revolutionary. But before Einstein arrived at this realization, a number of other brilliant minds were working on concepts that would lead him to his groundbreaking theory. One of the most important figures in this story is David Hilbert, a mathematician whose work in the early 20th century closely mirrored Einstein's own path. Hilbert's development of field equations, mathematical descriptions of the relationship between matter, energy, and the geometry of spacetime, was done almost simultaneously with Einstein's. In fact, some historians argue that Hilbert had arrived at the equations before Einstein did, though Einstein is generally credited with the final version due to his physical insights. Regardless of who was first, Hilbert's work was integral in formulating the mathematical language that Einstein would use to describe gravity in a completely new way. But the story doesn't stop there. Felix Klein, another towering figure in mathematics, also helped set the stage for Einstein's theories. Klein's work on the Klein-Gordon equation was foundational for what would eventually become quantum field theory. While Klein's work wasn't directly about gravity, his understanding of the behavior of fields in space laid important groundwork for the kind of mathematical thinking Einstein would later employ. In a sense, Klein helped show how mathematics could be used to describe the interactions between different fields, and that idea would play a crucial role in Einstein's thinking. The origins of Einstein's theories also involved the work of Henri Poincaré, who was one of the first to realize that the concept of space-time wasn't as absolute as people thought. While Poincaré didn't have a complete theory of gravity, he laid the groundwork for understanding that time and space were relative to the observer. His ideas about how space and time could interact, and how they could change depending on an observer's perspective, were key pieces in the puzzle that Einstein would eventually solve. In many ways, Poincaré suggested that the very fabric of space-time itself might be malleable, but it took Einstein to fully develop that insight into a comprehensive theory. As these brilliant minds were pushing the boundaries of physics, Ernst Mach was also contributing an important philosophical idea that influenced Einstein's thinking. Mach's principle suggested that the local motion of any object is influenced by the distribution of matter in the entire universe. Imagine that you're sitting in a car that's moving fast. If you suddenly turn, you feel the force pushing you to the side. According to Mach, the same thing happens with objects in space. What happens locally to one object is influenced by the entire mass of the universe. This idea would later inspire Einstein as he formulated his theory of gravity, suggesting that the curvature of space-time could be influenced not just by nearby objects, but by the entire cosmos. In this framework, gravity wasn't a force in the traditional sense. It wasn't like a magnet pulling on a piece of metal. Instead, gravity was seen as the result of the curvature of space-time caused by massive objects. Massive objects, like stars or planets, actually change the shape of space-time around them, and that curvature is what causes objects to move. Objects follow the curved path of space-time, which we perceive as gravitational attraction. Einstein's equations of general relativity mathematically describe how space-time curves, and how that curvature is related to the distribution of matter and energy in the universe. The central equation of general relativity is beautifully simple yet incredibly profound. It is written as g equals 8 pi t, where g represents the curvature of space-time, what we call the Einstein tensor, and t represents the distribution of mass and energy, the stress-energy tensor. This equation links the shape of space-time to the amount of energy and mass present. The greater the mass or energy, the more space-time bends. In this way, objects that move through this curved space-time will follow paths that are determined by the curvature, leading to what we feel as gravity. As Einstein's theory began to take shape, the implications for our understanding of space, time, and gravity became astonishing. One of the most intriguing consequences of general relativity is the idea of space-time singularities, regions where space-time curvature becomes infinite, and the laws of physics as we know them break down. The most famous example of a space-time singularity is the black hole, an object whose gravitational pull is so strong that nothing, not even light, can escape its grasp. The notion of black holes was first explored by John Archibald Wheeler, one of the great physicists of the 20th century, who is credited with coining the term black hole. Wheeler also proposed the idea of geons, hypothetical objects made of gravitational waves that could, in theory, exist as packets of energy. Geons were speculative, and while they've never been observed, they represent an interesting blending of classical ideas about gravity with the emerging theories of quantum mechanics. As fascinating as Einstein's equations are, they don't just describe what we can see. They open the door to phenomena we can only infer through the tools of modern physics. Gravitational waves are one of these phenomena, and they are a direct prediction of Einstein's theory. When massive objects like black holes or neutron stars accelerate or collide, they send ripples through the fabric of space-time itself. These ripples travel outward from their source, carrying with them information about the events that caused them. Gravitational waves provide a window into the universe's most extreme and violent processes, allowing us to study black holes, neutron stars, and other cosmic objects in ways we never could before. So, from the early seeds planted by Poincaré and Mach, to the revolutionary insights of Einstein, and the later contributions of scientists like Wheeler, the story of general relativity is one of collaboration across generations, fields, and ideas. Today, as we detect gravitational waves and peer deeper into the universe, we continue to build on this rich legacy of understanding, discovering more about the cosmos and the very fabric of space-time itself. When Albert Einstein first formulated his theory of general relativity, one of the most profound implications was the prediction of gravitational waves. These waves, subtle ripples in the fabric of space-time, were an inevitable consequence of his equations. But while Einstein's equations laid out the existence of these waves, they remained theoretical for decades. The story of their discovery is a fascinating journey that involves brilliant minds working in different fields and stretching the limits of what was thought possible. The concept of gravitational waves was first introduced by Einstein in 1916, shortly after he published his theory of general relativity. In this new framework, gravity was no longer a force transmitted through space. Instead, it was the curvature of space-time itself, caused by the presence of mass and energy. Einstein's equations described how space-time was shaped by these objects, and how that shape influenced the motion of everything else. These equations predicted that when massive objects like stars or black holes accelerated or collided, they would send out ripples, gravitational waves, through space-time. However, Einstein himself wasn't sure that these waves would ever be detected. The main issue was that gravitational waves are incredibly weak. Even when two black holes collide, sending out an enormous burst of energy, the actual effect on space-time here on Earth is tiny. In fact, the change in distance caused by a gravitational wave passing through Earth would be less than the width of a proton, far too small to detect with the technology of Einstein's time, but the idea that such waves existed opened a new chapter in theoretical physics, one that would require new mathematical tools and advanced concepts from other areas of physics. One of the key breakthroughs in making sense of gravitational waves came from Arnold Sommerfeld, a German physicist whose work helped extend Einstein's framework. Sommerfeld used a method called perturbation theory to examine the small changes in space-time caused by gravitational waves. In perturbation theory, complex systems are studied by considering them as small deviations from a simpler system. By applying this approach to general relativity, Sommerfeld helped pave the way for understanding how gravitational waves would behave and interact with their surroundings. While Sommerfeld's work focused on the mathematical side of things, other scientists were working on the broader implications of wave phenomena in physics. Max Born, for example, was instrumental in laying the foundations of quantum theory. He worked on the mathematical underpinnings of quantum mechanics, which describes the behavior of particles at the smallest scales. Although Born's work wasn't directly about gravitational waves, it provided the mathematical framework for understanding how different types of waves, including gravitational waves, might behave in the quantum world. Alongside Born, Hermann Weyl also made contributions to the early development of quantum theory, helping to establish concepts like wave functions and the idea of quantum fields. These ideas would later intersect with the study of gravitational waves, especially as scientists began to explore how quantum mechanics and general relativity might come together. But it wasn't until the mid-20th century that a truly revolutionary approach to wave phenomena would appear. Richard Feynman, one of the most influential physicists of the 20th century, developed a method known as the path integral approach to quantum field theory. Feynman's path integrals provide a way to calculate the probability of different outcomes in quantum systems by considering every possible path a particle could take. This approach was incredibly powerful because it could incorporate not just the classical laws of motion, but also the complex, unpredictable behavior of quantum systems. Feynman's work laid the groundwork for thinking about gravitational waves in a new way. In quantum mechanics, particles are described not just by specific positions or velocities, but by a range of possible states that evolve over time. When applied to gravitational waves, this framework suggested that they could also exhibit quantum behavior. Could gravitational waves, like particles, have quantum states? Would they follow paths determined by probabilities rather than deterministic rules? This question remains one of the fascinating frontiers of research today. But even though the theoretical foundation for gravitational waves was established early on, detecting them remained an enormous challenge. Theoretical physicists were able to predict that gravitational waves should exist, and they even understood how they should behave. But how could they measure these minuscule effects? This is where the work of Willem de Sitter, a Dutch astronomer and mathematician, comes into play. De Sitter explored solutions to Einstein's equations that applied to expanding universes, contributing to the broader understanding of how gravitational waves might propagate across vast distances in an ever-expanding cosmos. While De Sitter didn't directly address the detection of gravitational waves, his work on cosmology helped set the stage for later thinking on how gravitational waves might be observed as they travel through space. The difficulty in detecting gravitational waves led many to believe that it might never be possible to observe them directly. Even after decades of theoretical development, the faintness of the waves meant that detecting them was an immense technical challenge. It was not until the late 20th century that a breakthrough in technology would make the detection of gravitational waves a real possibility. This breakthrough came in the form of LIGO, the Laser Interferometer Gravitational Wave Observatory, which was designed to measure the tiny distortions in spacetime caused by passing gravitational waves. But before LIGO could become a reality, physicists like Gerard 't Hooft were already beginning to explore the connection between quantum mechanics and gravitational waves. 't Hooft, a Nobel laureate known for his work in quantum gravity, explored the ways in which quantum mechanics might intersect with general relativity. One of the key ideas he proposed was that quantum effects could influence spacetime itself, making it possible for gravitational waves to behave in ways that could be understood through the language of quantum mechanics. This idea, connecting the quantum world with the fabric of spacetime, has become a major theme in modern theoretical physics, and is one of the reasons why gravitational waves are so much more than just a curiosity. They are a potential key to unlocking the mysteries of quantum gravity, the long-sought theory that would unify quantum mechanics with general relativity. Through the contributions of these brilliant minds, the path to the detection of gravitational waves became clearer, though still fraught with challenges. Their theoretical understanding of space-time waves and the quantum world all combined to create the groundwork for a new branch of science, gravitational wave astronomy. Today, thanks to their work, we can observe the ripples in space-time caused by the most violent and energetic events in the universe, events like the merger of two black holes, which sent waves through space-time that were detected by LIGO in 2015. In many ways, the discovery of gravitational waves was the culmination of a century of work, beginning with Einstein's equations and continuing through the contributions of countless physicists and mathematicians. It was a moment that validated the predictions of general relativity, showing that the most elusive aspects of Einstein's theory, such as the bending of space-time, could be measured and studied directly. But the story doesn't end there. The discovery of gravitational waves opens up a new chapter in our understanding of the universe, and the work of those early pioneers is still guiding the way forward. The story of detecting gravitational waves hinges not only on understanding the vastness of space-time, but also on harnessing the subtleties of quantum mechanics. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, is at the forefront of this groundbreaking achievement. LIGO is a marvel of modern engineering and physics, capable of detecting distortions in spacetime smaller than the width of a proton. But to achieve this extraordinary feat, LIGO's design and function are deeply tied to quantum principles first laid out by brilliant minds like John Bell and Werner Heisenberg. Let's start by understanding the challenge. Gravitational waves are incredibly weak, even when they are the result of cosmic events like the collision of two black holes. These waves stretch and compress space-time by an infinitesimally small amount. In fact, a passing gravitational wave might cause a change in the length of LIGO's arms, each measuring 4 kilometers, by less than 1,000th of the width of a proton. Such a minuscule fluctuation requires technology capable of detecting changes on an incredibly precise scale. Here is where John Bell and his work on quantum mechanics become relevant. In the mid-20th century, Bell introduced the concept of hidden variables, which proposed that quantum systems might have underlying properties, unobserved variables, that could explain their behavior. Bell's theorem, published in 1964, showed that quantum mechanics, with its inherent uncertainty, could not be explained by hidden variables in a way that aligned with the predictions of classical physics. His work deepened our understanding of quantum systems and highlighted that quantum phenomena, such as the behavior of light and particles, were inherently probabilistic, not deterministic. This principle has profound implications for LIGO. The very act of measuring gravitational waves is rooted in quantum mechanics. LIGO uses laser interferometry, a technique where a laser beam is split into two and sent along two arms. When the laser beams are recombined, the light creates an interference pattern. This pattern changes when gravitational waves pass through, causing a shift in the distances between the mirrors that reflect the laser beams. The problem is that these measurements are so small that the precision required is affected by quantum fluctuations, tiny random movements that arise from the quantum nature of light and mirrors. These fluctuations were part of the design challenge that scientists had to overcome. One of the key concepts in quantum mechanics that influences this process is the Heisenberg uncertainty principle, which states that there is a fundamental limit to how precisely we can know certain pairs of properties of a system, such as its position and momentum, at the same time. In the case of LIGO, this principle sets a limit on how precisely we can measure the position of the mirrors that detect gravitational waves. If you measure the position too precisely, you introduce uncertainty in the measurement of the mirror's momentum and vice versa. This creates a fundamental challenge in detecting gravitational waves, as the act of measuring them disturbs the system slightly, just by virtue of quantum mechanics. The engineers behind LIGO, including Rainer Weiss, realized that this challenge could be addressed by carefully controlling the quantum noise. Weiss, along with others, worked on improving the sensitivity of interferometers, the technology that forms the heart of LIGO. Interferometers work by splitting a beam of light, sending it along two paths, and then recombining the beams to observe their interference pattern. If a gravitational wave passes through, it alters the distances along these two arms, changing the interference pattern. The key challenge is to detect changes in this pattern so incredibly small that the typical quantum noise in the system doesn't obscure the signal. Weiss's contributions to designing interferometers with unprecedented precision were critical to LIGO's success in detecting gravitational waves. Weiss, who is often credited with the idea of using interferometry for gravitational wave detection, worked tirelessly alongside Kip Thorne and Barry Barish to bring this vision to life. Thorne, a Nobel laureate and a pioneer in gravitational wave physics, had long advocated for building detectors sensitive enough to measure these minuscule waves. His deep understanding of space-time, black holes, and gravitational waves helped lay the theoretical foundation for LIGO's design. It wasn't just about detecting gravitational waves, but about making sure LIGO could do so with the utmost sensitivity. As LIGO moved toward its first successful detection, the fundamental principles of quantum mechanics and the uncertainty principle were still very much in play. The key to overcoming these challenges was to carefully balance the quantum noise and to design the interferometer in such a way that it minimized the influence of random quantum fluctuations. One of the most exciting developments in quantum mechanics and gravitational wave detection is the potential for quantum-enhanced sensors. Researchers like Andrew Cleland and John M. Martinez have explored the possibility of using quantum computing and quantum-enhanced sensors to make measurements even more precise. In particular, Cleland and Martinez proposed using quantum algorithms to reduce the impact of quantum fluctuations, allowing for more sensitive and accurate measurements of gravitational waves. This represents an exciting future direction for gravitational wave detection, where the quantum properties of the instruments themselves could be manipulated to improve performance. Niels Bohr, a foundational figure in quantum mechanics, contributed to another key aspect of quantum measurement, the complementarity principle. This principle suggests that objects like light or particles can exhibit both wave-like and particle-like behavior, depending on how they are measured. In LIGO's case, the measurement of gravitational waves involves not just the interference of light waves, but also the careful measurement of the wave's particle-like properties. Bohr's complementarity principle provides a philosophical foundation for understanding this wave-particle duality in the context of quantum measurements, helping to guide the design and interpretation of LIGO's data. When LIGO detected its first gravitational wave in 2015, it was the culmination of decades of work based on these quantum mechanical principles. The success of LIGO was not just a triumph of engineering, but also a testament to how deeply quantum mechanics is intertwined with the detection of gravitational waves. The process of measuring gravitational waves involved the precise manipulation of light, mirrors, and sensors at scales so small they border on the quantum realm. And as we look toward the future, quantum-enhanced sensors may allow us to make even finer measurements, helping to unlock more secrets of the universe. LIGO's ability to measure gravitational waves, and do so with the incredible precision required, has opened a new era in astrophysics. Gravitational wave astronomy is still in its early stages, But the combination of classical ideas about space-time with quantum mechanical principles has created a powerful new tool for exploring the universe. As technology advances and our understanding of quantum mechanics deepens, we may see a new generation of detectors that push the boundaries even further. The discovery of gravitational waves was just the beginning, and with the help of quantum mechanics, the next steps in this journey promise to be even more astonishing. On September 14, 2015, a faint signal reached Earth that would change the course of scientific history. This signal, detected by the Laser Interferometer Gravitational Wave Observatory, or LIGO, was the first ever direct detection of gravitational waves, ripples in the very fabric of space-time caused by the collision of two black holes, each weighing several times more than our Sun. The discovery of this signal, known as GW 150914, was more than just a scientific milestone. It was a profound moment that brought the theory of general relativity to life in a way never before seen, and it opened a new chapter in our understanding of the universe. But to fully appreciate the significance of GW 150914, we must look beyond the mere detection of these waves and consider the broader implications for both cosmology and our understanding of physics itself. The detection marked the moment when theoretical predictions that had existed for over a century, were no longer just abstract ideas. Gravitational waves were real, detectable, and could now be used to probe some of the most extreme events in the cosmos. The discovery was not just a triumph of technology, it was also a philosophical shift, a new way to look at the universe. Before the detection, gravitational waves had been a theoretical curiosity. Albert Einstein first predicted them in his general theory of relativity in 1916, but their detection seemed almost impossible. The waves, caused by events like the merger of two black holes, are so tiny that they distort spacetime by less than 1,000th of the diameter of a proton. How could anything detect such an infinitesimal change, especially with all the background noise from the Earth itself? Yet, despite the challenges, LIGO succeeded. One of the key people in making this success possible was B.F. Schutz, a physicist whose work on data analysis techniques for gravitational wave astronomy helped to make this detection possible. Schutz was instrumental in developing the methods that would allow scientists to distinguish between real gravitational wave signals and the vast amounts of noise generated by the Earth, seismic activity, and other sources. His techniques helped refine the signals and allowed LIGO to recognize the characteristic chirp of a gravitational wave, a distinct pattern caused by two objects spiraling toward each other before merging. This detection also raised deeper philosophical and cosmological questions. Gravitational waves are, at their core, a manifestation of the curvature of space-time. In this sense, they bring us closer to understanding the very fabric of the universe. To put this in perspective, gravitational waves are not just an echo of distant events. They are a direct link to the most violent phenomena in the universe, events that shape and mold space-time itself. What makes these waves so fascinating is that they provide a bridge between two realms of physics, the quantum and the classical. For decades, physicists have struggled to reconcile the behavior of the very small, particles and quantum systems, with the behavior of the very large, planets, stars, and galaxies. The detection of gravitational waves presents an opportunity to explore this connection further. To understand this, we can turn to the ideas of Roger Penrose, a mathematician and physicist whose work on the geometry of spacetime has provided deep insights into the nature of the universe. Penrose's ideas about spacetime singularities, regions where the curvature of spacetime becomes infinite, such as the center of a black hole, are central to understanding the behavior of gravitational waves. In classical general relativity, a singularity represents a point where the laws of physics break down. But in the quantum world, where uncertainty reigns, things might behave differently. Gravitational waves give us a new tool to probe these singularities, allowing us to study them in ways that were previously impossible. As these waves travel across the universe, they carry information about the objects that created them, information that could eventually help us unite the quantum and classical worlds. Another key figure in understanding the implications of gravitational waves is Matthew Hedrick, whose work on black hole thermodynamics has provided important insights into the behavior of black holes and the radiation they emit. Black holes are strange objects, where gravity is so intense that not even light can escape. Yet black holes are not just cosmic vacuum cleaners, They can emit radiation in the form of Hawking radiation, a phenomenon first proposed by Stephen Hawking. This radiation, which arises due to quantum effects near the event horizon of a black hole, can be linked to the entropy of the black hole, the measure of its information content. By studying gravitational waves emitted by black hole mergers, scientists can learn more about black hole entropy and test the limits of our understanding of thermodynamics in extreme environments. The implications of gravitational wave detection extend far beyond black holes. One of the most exciting possibilities is what these waves might reveal about the very structure of space-time itself. The detection of GW 150914, for example, not only confirmed that black holes exist, but also provided new insights into the masses of these objects and how they behave as they spiral toward one another. But the real excitement lies in the potential for future discoveries. Could gravitational waves reveal hidden dimensions of space-time, or even prove the existence of phenomena like dark matter or dark energy? This is where the holographic principle comes into play. The holographic principle, proposed by the physicist Juan Maldacena in the late 20th century, suggests that the entire universe might be understood as a projection from a lower dimensional boundary. In other words, everything we experience as three-dimensional space and time might be a projection of information encoded on a two-dimensional surface. If this idea is correct, gravitational waves might provide a key to unlocking the nature of this boundary and understanding the true structure of the universe. Gravitational waves could reveal new layers of the cosmos, layers that challenge our understanding of space, time, and reality itself. In a similar vein, Raphael Bousso has contributed to the study of cosmology and the boundary structure of space-time. His work on the holographic principle and cosmological horizons suggests that our understanding of the universe might be incomplete without considering the limits of space-time. Gravitational waves, in this context, become more than just signals. They become a tool for testing and refining these abstract ideas about the nature of space and time. The detection of GW 150914 also opens the door to future discoveries that could deepen our understanding of black hole dynamics, the geometry of space-time, and the fundamental nature of gravity. As gravitational wave astronomy continues to develop, we may begin to explore even more extreme events, like the merger of neutron stars or the birth of new black holes, that could shed light on the mysteries of the universe. In the end, the detection of gravitational waves isn't just about observing distant cosmic events. It's about using these waves as a tool to explore the very nature of the universe itself. As we continue to study the ripples in space-time caused by events like black hole mergers, we may uncover deeper truths about the cosmos, truths that challenge our ideas of space, time, and reality. The discovery of GW 150914 was just the beginning, and as our ability to detect and understand gravitational waves improves, the universe may soon reveal even more of its most hidden secrets. Black hole mergers are among the most extreme and fascinating events in the universe. When two black holes collide, the resulting explosion sends out ripples through space-time, producing gravitational waves that can travel across the cosmos, carrying with them information about the merger itself. These violent mergers are the primary sources of gravitational waves that we detect here on Earth, and they offer us a unique opportunity to probe some of the most mysterious and enigmatic objects in physics, the black holes and their singularities. To fully appreciate the significance of these mergers, we must first understand what happens when black holes collide. At the heart of a black hole lies the singularity, a point where the gravitational pull is so strong that not even light can escape. The laws of physics as we know them break down inside this point, making singularities a profound mystery. Black hole mergers allow us to study these singularities in a way that was previously unimaginable, as they offer a glimpse into the heart of one of the most extreme regions of space-time. But before we delve deeper into the physics of black hole mergers, it's important to consider the work of Roger Penrose, who helped lay the groundwork for understanding the behavior of black holes. In 1969, Penrose proposed the idea of the Penrose process, a mechanism through which energy can be extracted from a black hole. According to this process, particles falling into a black hole can split into two, with one particle being absorbed by the black hole and the other escaping into space. The escaping particle carries away energy, which can theoretically be harnessed. This idea was a key step in understanding how black holes interact with their surroundings, and it also helped shape our understanding of the extreme conditions at the event horizon. the boundary beyond which nothing can escape a black hole's pull. The Penrose process is fascinating in its own right, but it also lays the groundwork for understanding the gravitational wave signals produced during black hole mergers. As two black holes spiral toward each other and eventually merge, they release a tremendous amount of energy in the form of gravitational waves. These waves carry information about the black hole's masses, spins, and the way in which they collided. The first direct detection of gravitational waves, GW 150914, was caused by the merger of two black holes, and it offered us our first real insight into the behavior of these enigmatic objects. As we study black hole mergers and their associated gravitational waves, it becomes clear that these events could also provide a way to probe deeper into the nature of spacetime itself. One of the exciting prospects is the possibility of detecting quantum gravitational effects during these mergers. Carlo Rovelli, one of the leading proponents of loop quantum gravity, has developed a framework that suggests that spacetime itself is not smooth and continuous, as described by Einstein's theory of general relativity, but instead is made up of discrete quantum units. This approach challenges our classical understanding of spacetime and offers a new way of thinking about gravity at the smallest scales. If loop quantum gravity is correct, black hole mergers could provide a unique window into the quantum nature of spacetime. The extreme conditions during a black hole merger, where both quantum mechanics and general relativity come into play, could reveal new insights into how gravity works at the quantum level. This intersection between quantum mechanics and general relativity is one of the most exciting frontiers in theoretical physics, and gravitational wave astronomy may offer us the tools to explore it further. While loop quantum gravity offers one possible view of the universe at the smallest scales, there are also other theories that suggest spacetime could be more complex than we currently understand. One such theory is string theory, which posits that the fundamental particles of the universe are not point-like objects, but rather tiny vibrating strings of energy. According to string theory, the universe has additional spatial dimensions beyond the three that we experience. These extra dimensions could play a crucial role in understanding the physics of black holes and gravitational waves. The work of Edward Witten, one of the leading theorists in string theory, has suggested that higher dimensional models of the universe might offer a new explanation for the underlying physics of black holes. If spacetime is truly higher dimensional, the gravitational waves produced by black hole mergers could carry signatures of these extra dimensions. Detecting these signatures would not only deepen our understanding of black holes, but could also help reveal the fundamental structure of spacetime itself. String theory may provide the key to understanding how gravity operates at both the quantum and cosmological scales, and gravitational wave astronomy could be an essential tool in testing these ideas. Another fascinating aspect of black holes and gravitational waves comes from the work of Andrew Strominger, who has proposed the idea of soft hair on black holes. In classical physics, black holes are often thought of as featureless objects, defined only by their mass, charge, and spin. But Strominger's work suggests that black holes may actually have additional, subtler properties, which he referred to as soft hair. These are the quantum states that could be encoded on the surface of a black hole, similar to how the detailed properties of a system can be encoded in the configuration of its components. Strominger's idea is important because it could offer a new way of understanding the gravitational wave signals emitted by black holes. If black holes have soft hair, then the gravitational waves they produce might carry additional information about the black hole's quantum properties. This could open up a new way of studying the quantum nature of black holes and help us understand the complex dynamics at play during a black hole merger. It also presents a fascinating twist on the traditional black hole theory, suggesting that these objects are not as simple as we once thought, but may contain hidden layers of quantum information that can be unlocked through the study of gravitational waves. The potential for black hole mergers to reveal new insights into the nature of spacetime, quantum mechanics, and gravity is immense. By studying the gravitational waves produced by these mergers, we may be able to test and refine our theories of the universe, from quantum gravity to string theory and everything in between. As our technology improves and our understanding of these phenomena deepens, we may find that black hole mergers offer far more than just a glimpse into the behavior of the universe's most extreme objects. They may provide the key to unlocking some of the deepest mysteries of physics itself. In the coming years, as gravitational wave detectors become more sensitive and new theoretical frameworks emerge, the quest to understand black holes and their mergers will continue to drive our exploration of the cosmos. With each new detection, we move one step closer to uncovering the true nature of these cosmic giants and the secrets they hold about the universe we live in. Neutron stars are some of the most fascinating and extreme objects in the universe. Born from the collapse of massive stars in supernova explosions, neutron stars pack a mass greater than the Sun into a sphere only a few kilometers across. The result is an incredibly dense object, with a gravitational pull so strong that it warps spacetime itself. The behavior of these strange stars, particularly when they merge, is a key source of gravitational waves, which we now observe with ever-increasing precision. When two neutron stars collide, they send out ripples through spacetime that we can detect here on Earth. This kind of merger is a significant source of gravitational waves, and it provides an extraordinary opportunity to study not only the properties of neutron stars, but also the behavior of spacetime in the most extreme environments. The energy released during such a merger is colossal, and the gravitational waves carry information that tells us about the masses, spins, and the dynamics of these dense objects. The study of neutron stars and their mergers is deeply tied to George Gamow, a pioneering physicist and cosmologist. Gamow's work in the field of nuclear astrophysics provided the theoretical groundwork for understanding how elements are formed in stars and during supernovae. His research in the 1930s and 40s contributed to our understanding of how stars explode and how their remnants, like neutron stars, could form under extreme conditions. These remnants, as it turns out, are central to the generation of gravitational waves. Gamow's work on the nuclear processes that occur in stellar explosions helps explain the violent environments that give birth to neutron stars and other exotic objects, providing context for understanding the powerful waves that these objects emit. But perhaps one of the most groundbreaking contributions to our understanding of neutron stars came in 1967, when Jocelyn Bell Burnell, a young astronomer, discovered the first pulsar. Pulsars are rapidly rotating neutron stars that emit beams of electromagnetic radiation, and their discovery opened up a whole new way of studying the universe. What made pulsars so intriguing was their regular periodic signal, which was unlike anything ever observed before. Bell Burnell's discovery not only helped confirm the existence of neutron stars, but also provided new tools for measuring their properties and studying the surrounding space. Her work, though initially met with skepticism, ultimately transformed our understanding of these objects and led to further discoveries, including neutron star mergers and the resulting gravitational waves. Kip Thorne, a Nobel laureate in physics, has made significant contributions to understanding the astrophysical importance of neutron star collisions and the gravitational waves they produce. Thorne's work on the dynamics of gravitational waves and his studies of the interactions between stars, black holes, and neutron stars were instrumental in predicting the kinds of signals we would observe when neutron stars merge. In particular, Thorne's research on the energy and frequency of gravitational waves from such mergers helped refine the designs for detectors like LIGO. He was one of the key scientists who realized that these events could be detected and analyzed, providing a direct way to probe the very nature of space-time. The collision of neutron stars is not just a cosmic event, it's a natural laboratory for testing theories about gravity, mass, and the fundamental properties of the universe. When two neutron stars collide, the result is often a kilonova, a rare but incredibly bright explosion that occurs when the intense gravitational and nuclear forces release huge amounts of energy. Kilonovae are believed to be the source of heavy elements like gold and platinum, which are formed in the extreme conditions created by the neutron star merger. This understanding of kilonovae has been crucial in linking gravitational waves to the creation of these precious metals. The discovery of a kilonova, following the detection of gravitational waves from the neutron star merger GW 170817 in 2017, confirmed that these events are responsible for creating some of the heaviest elements in the universe. This groundbreaking discovery not only validated the connection between gravitational waves and astrophysical phenomena like kilonovae, but it also provided a new way to study the origins of the elements we find on Earth. The study of neutron star mergers, however, is not limited to the understanding of these objects themselves. It also has broader implications for the field of theoretical physics. One of the most exciting possibilities is that studying neutron stars could reveal more about quantum gravity, the field of physics that seeks to merge the principles of general relativity with quantum mechanics. While general relativity describes the large-scale structure of spacetime, and quantum mechanics explains the behavior of particles at the smallest scales, the two frameworks have yet to be unified into a single theory that explains all of physics. Neutron star mergers, where both quantum and relativistic effects are significant, could be the key to bridging this gap. One approach to quantum gravity comes from loop quantum gravity, a theory that proposes that spacetime itself is quantized, composed of discrete chunks rather than being smooth and continuous as general relativity suggests. Carlo Rovelli, one of the leading proponents of this theory, has suggested that the extreme conditions of a neutron star merger might provide evidence for these quantum effects in spacetime. As gravitational waves travel through space and interact with the structures of spacetime, they could reveal whether spacetime behaves as a continuous or discrete entity. Detecting such quantum gravitational effects in the context of neutron star mergers would be a groundbreaking discovery, offering new insights into the very nature of space and time. In addition to loop quantum gravity, string theory offers another potential framework for understanding the universe at its most fundamental level. String theory proposes that the fundamental particles of nature are not point-like objects, but rather tiny vibrating strings of energy. These strings may vibrate in more than the three spatial dimensions we are familiar with, suggesting that the universe has additional hidden dimensions. Edward Witten, one of the most influential figures in string theory, has suggested that higher dimensional models of spacetime might help explain the behavior of black holes and neutron stars. In these models, gravitational waves might reveal signatures of higher dimensional physics, providing a window into the true structure of the universe. If such effects are detected in the gravitational waves emitted by neutron star mergers, it could be a major breakthrough in our understanding of physics. The study of neutron star mergers and their gravitational waves continues to evolve, and the search for even more exotic sources of gravitational waves is just beginning. One intriguing possibility comes from the study of cosmic strings, hypothetical one-dimensional objects that might have formed in the early universe. These cosmic strings could create gravitational waves as they move through space, and some theorists, like Alexander Vilenkin, have suggested that they could be detected by advanced gravitational wave observatories. While cosmic strings remain theoretical, the possibility of detecting their gravitational wave signatures could provide a unique glimpse into the early universe, offering valuable clues about the fundamental forces that shaped our cosmos. As we continue to study neutron stars and other exotic sources of gravitational waves, we are uncovering more about the universe's most extreme and fascinating objects. From the origins of heavy elements in kilonovae to the potential for detecting quantum gravitational effects, these phenomena offer a unique opportunity to explore the deepest mysteries of space and time. As technology improves and our understanding deepens, the study of neutron star mergers and other gravitational wave sources will continue to reshape our understanding of the universe, revealing new layers of cosmic complexity and helping to bridge the gap between classical and quantum physics. For more than a century, Einstein's general theory of relativity has been our best description of gravity, explaining everything from the fall of an apple, to the motion of planets, to the bending of light by massive objects. It's one of the most successful theories in the history of science, standing up to rigorous tests and observations time and time again. But as with all theories, general relativity doesn't claim to be the ultimate answer. In fact, there are alternative theories that could modify or extend Einstein's theory, offering new perspectives on gravity and the nature of the universe. And interestingly, these alternative theories could be tested using the very same gravitational waves that Einstein's theory predicted, providing us with a powerful tool to explore whether general relativity is the final word, or whether we're still missing a deeper understanding. One of the first alternative theories to gain attention is modified Newtonian dynamics, or MOND, proposed by the Israeli physicist Mordechai Milgram in the 1970s. MOND was introduced to address a long-standing issue in astronomy: the observed discrepancy between the amount of visible matter in galaxies and the gravitational effects that are observed. Specifically, the rotation speeds of galaxies are much faster than expected based on the amount of visible mass in them. In a traditional Newtonian framework, galaxies would be expected to spin more slowly, because the gravitational pull of their visible matter wouldn't be enough to account for the speeds that we observe. Milgram proposed that the laws of gravity might not follow the simple inverse square law at very small accelerations, those found at the edges of galaxies. Instead, gravity could become stronger than expected at these low accelerations, providing an explanation for the high rotation speeds without invoking dark matter. MOND is a fascinating modification to Newtonian gravity, suggesting that our understanding of gravitational forces might need adjustment when applied to galaxies and smaller scales. However, the theory has its limits, especially when it comes to large-scale cosmology and the behavior of gravitational waves. So where does MOND fit into the world of gravitational wave astronomy? Since gravitational waves are directly related to the curvature of spacetime, they can provide a crucial test for theories like MUND. If MOND accurately describes the behavior of gravity in the outskirts of galaxies, it could also influence how spacetime behaves when massive objects like neutron stars and black holes collide. By studying gravitational waves from these events, we could determine whether MOND might offer a better explanation for certain gravitational anomalies. So far, though, general relativity remains the best model to explain these waves, but MOND continues to be an area of exploration that could yield valuable insights in the future. Beyond MOND, other theories take a more radical approach by suggesting that gravity might not be the only force acting on large scales. M-theory and supergravity are two such theories that extend our understanding of the fundamental forces by proposing the existence of additional dimensions beyond the familiar three spatial dimensions and one time dimension that we experience. These theories build on string theory, which posits that the fundamental particles of the universe are not point-like objects but rather tiny, vibrating strings of energy. According to M-theory, these strings might vibrate in more than the 4 dimensions we know, with up to 11 dimensions proposed in some models. Edward Witten, one of the leading proponents of string theory and M-theory, has suggested that these extra dimensions could have a significant effect on gravity. The gravitational waves produced by black hole mergers or neutron star collisions could, in theory, carry signatures of these higher dimensions. For instance, the way spacetime bends and stretches during such cataclysmic events might reveal clues about the existence of additional dimensions, which could open up new ways of thinking about gravity, spacetime, and the fundamental structure of the universe. Detecting these signatures through gravitational wave astronomy would not only confirm the existence of extra dimensions, but also help to refine our understanding of how gravity behaves at both large and small scales. One of the more intriguing aspects of gravitational wave research in the context of higher dimensional theories is the potential to detect subtle signals from the early universe. String cosmology, a branch of string theory, proposes that the very early universe could have been governed by higher dimensional physics. Events from this early universe, including the formation of black holes or other exotic objects, might leave faint traces in the gravitational wave background. These faint ripples could provide evidence for higher dimensional physics and offer a window into the conditions of the universe just moments after the Big Bang. While the direct detection of such early universe signals is still a distant goal, the study of gravitational waves may eventually shed light on these deep, fundamental questions about the cosmos. Another exciting avenue of exploration involves the concept of a fifth force in nature, an additional force that could modify our understanding of gravity. The 4 known fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, are typically well understood and well tested. But some theories suggest the possibility of a fifth force, one that could explain certain gravitational anomalies or offer a new understanding of the universe's expansion, dark energy, and dark matter. One physicist contributing to this idea is Alexei Frolov, whose work in theoretical physics examines how non-Newtonian forces could influence gravitational interactions, particularly at cosmic scales. Frolov's research suggests that, in certain extreme environments, gravitational waves could carry signatures of a fifth force, offering insight into forces beyond the ones we know. If this new force does exist, detecting its effects through gravitational waves could have profound implications for both our understanding of gravity and the way we view the universe as a whole. Gravitational waves, therefore, could provide a crucial test for theories that predict such forces, making them a valuable tool in the search for new physics. Finally, let's consider the work of Lee Smolin, a physicist known for his ideas on the evolution of the laws of physics. Smolin has proposed that the laws of physics might not be fixed but could evolve over time, influenced by the conditions of the universe itself. This evolutionary view of physics challenges our understanding of the constancy of physical laws and opens up new avenues for testing the foundations of gravity and cosmology. The detection of gravitational waves, especially from extreme events like black hole mergers, could provide a testing ground for Smolin's ideas. If the laws of gravity are indeed evolving, then the way gravitational waves propagate and interact could provide evidence for this dynamic process, reshaping our understanding of the universe's evolution. As we continue to push the boundaries of gravitational wave astronomy, the possibility of uncovering new theories and discovering unknown forces is an exciting prospect. Whether through testing alternative theories of gravity like muon, exploring the implications of higher dimensions in string theory, or searching for signatures of a fifth force, gravitational waves offer us an unparalleled opportunity to test the limits of our understanding. The future of gravitational wave research holds immense promise, and with each new discovery, we move closer to answering some of the most profound questions about the nature of the universe. The detection of gravitational waves has been one of the most exciting breakthroughs in modern physics, allowing us to directly observe the ripples in spacetime caused by some of the universe's most energetic events, like the collision of black holes and neutron stars. But what if the discovery of these waves could reveal something even more profound, something beyond our own universe? What if gravitational waves could offer a glimpse into the existence of other universes, a multiverse with its own set of physical laws and realities? While this may sound speculative, it opens up a fascinating possibility that the study of gravitational waves could offer us clues about a deeper, more complex structure of reality than we've ever imagined. To understand how gravitational waves might support or challenge the existence of the multiverse, it's helpful to start with the multiverse theory itself. The idea that our universe might be just one of many is not new, but it has gained increasing attention in recent decades, especially in the fields of cosmology and quantum mechanics. At its core, the multiverse hypothesis suggests that there may be multiple universes, each with its own set of physical laws, constants, and even dimensions. Some of these universes could be vastly different from our own, while others might closely resemble ours. One of the leading proponents of multiverse theory is David Deutsch, a theoretical physicist known for his work on quantum mechanics and quantum computing. Deutsch's theory of the multiverse is built on the foundation of quantum physics, particularly the many-worlds interpretation. According to this interpretation, every time a quantum event occurs, such as an electron being in one place or another, the universe splits, creating a new branch of reality. In this view, every possible outcome of a quantum event exists in a separate universe, which means that our reality is just one of countless others that arise from these quantum branches. Now, imagine if gravitational waves could provide a way to detect these other universes. While it's still a highly speculative idea, some physicists have proposed that gravitational waves from other universes could leave traces in our space-time. If multiple universes exist and are interacting in some way with our own, their gravitational waves could potentially merge with or influence the waves we observe. This opens up an entirely new realm of possibilities, where gravitational wave astronomy could not only reveal information about objects in our own universe, but also offer a way to study the connections between universes. One of the most intriguing ideas in multiverse theory is Max Tegmark's classification of the multiverse. Tegmark, a cosmologist and physicist, proposed a detailed framework in which different types of multiverses exist, each with different properties. In his view, there are 4 levels of multiverses. The first level consists of the possibility of other universes existing in the same space but with different initial conditions. The second level involves the idea that different universes can have different physical laws, such as varying constants of nature or even different dimensions. The third level involves the multiverse as a consequence of cosmic inflation, where multiple regions of space expand at different rates and become separate universes. The fourth level, arguably the most speculative, suggests that there might be a multiverse formed by all possible mathematical structures, including those that do not resemble our own universe at all. In the context of gravitational wave astronomy, the second level of Tegmark's multiverse, where different universes could have distinct physical laws, holds particular promise. Gravitational waves are caused by the movement of mass and energy through space-time, and if other universes have different laws, their space-time could behave differently as well. This could potentially lead to gravitational waves with signatures distinct from what we would expect in our own universe. Detecting these waves would not only challenge our understanding of gravity, but could provide evidence for the existence of universes with different laws of physics, offering direct support for Tegmark's multiverse theory. Another prominent figure in the field of string theory, Brian Greene, has also contributed to our understanding of how the multiverse might exist. Green, known for his popular books on theoretical physics, has worked extensively on string theory, which posits that the fundamental particles of the universe are not point-like objects, but rather tiny vibrating strings of energy. One of the consequences of string theory is the idea that there may be additional dimensions beyond the three we experience. In some models, these extra dimensions could give rise to different types of universes, each with its own unique set of physical laws. In this framework, gravitational waves could reveal information about these hidden dimensions, potentially offering us a way to detect and study other universes. If gravitational waves from other universes exist, they might carry signatures of the different physical laws and constants that govern those universes. For example, a universe with different constants for gravity or electromagnetic forces might produce gravitational waves with different frequencies or patterns. Detecting these anomalies in gravitational wave signals could provide a way to distinguish between our own universe and others, offering indirect evidence for the existence of the multiverse. Looking ahead, the future of gravitational wave astronomy holds immense potential for advancing our understanding of the multiverse. As technology continues to improve, future gravitational wave observatories will become more sensitive, capable of detecting even fainter and more distant waves. With these advances, it may become possible to observe gravitational wave signals from beyond our own universe, potentially opening a window into the realms of the multiverse. One exciting possibility is the detection of gravitational waves from the early universe, from a time before the formation of the first stars or galaxies. These waves could carry information about the conditions of the universe shortly after the Big Bang, a time when the laws of physics were still forming. Some physicists have speculated that if the multiverse exists, the early universe could have been influenced by other universes, with their gravitational waves imprinting subtle effects on our own. This could provide a direct link between the multiverse and our observable universe, allowing us to test theories about the multiverse by studying the earliest moments of cosmic history. As gravitational wave astronomy evolves, the potential to explore deeper into the nature of reality itself becomes more tangible. The ability to observe signals from other universes would not only revolutionize our understanding of physics, but could also provide profound philosophical insights into the nature of existence. Are we truly alone in our universe, or are we just one of countless other realities, each with its own distinct laws and properties? Gravitational waves may one day help answer this question, giving us a deeper understanding of the cosmos and our place within it. In the end, gravitational waves represent more than just ripples in space-time. They are the key to unlocking some of the most fundamental questions in physics and cosmology. Whether they support or challenge the existence of the multiverse, their study promises to reshape our understanding of reality itself, pushing the boundaries of what we know and opening up new frontiers of discovery. The future of gravitational wave astronomy is bright, and it may one day reveal a universe far more complex and interconnected than we ever imagined. The discovery of gravitational waves marked a new era in our understanding of the universe, providing a direct way to observe the most violent and energetic events in the cosmos. However, these waves are not just a cosmic curiosity. They also offer an unprecedented opportunity to probe one of the most profound and unresolved questions in physics. How does gravity work at the quantum level? The intersection of quantum mechanics and gravitational waves lies at the cutting edge of theoretical physics, in the realm of quantum gravity. At the heart of quantum gravity is the attempt to unite two pillars of modern physics, general relativity and quantum mechanics. General relativity, formulated by Albert Einstein in 1916, is our best theory of gravity, and describes how massive objects warp space-time. It works incredibly well on large scales, explaining everything from the motion of planets to the behavior of black holes. However, when we zoom into the very small scales, where quantum mechanics rules, general relativity begins to break down. Quantum mechanics, on the other hand, governs the subatomic world, dealing with particles, energy, and forces at scales far smaller than atoms. It's an incredibly successful theory that explains everything from the behavior of electrons in atoms to the interactions of fundamental particles. The problem is that these two theories don't seem to fit together. While general relativity treats space-time as a smooth, continuous fabric, quantum mechanics suggests that at very small scales, space and time themselves might be quantized, made up of discrete units. This conflict between the two theories is one of the greatest challenges in modern physics, and resolving it is where the field of quantum gravity comes in. Quantum gravity seeks to merge the two frameworks into a single unified theory. One of the most influential figures in the development of quantum gravity was John Wheeler, a physicist who made groundbreaking contributions to both quantum mechanics and general relativity. Wheeler famously said, "Spacetime tells matter how to move, matter tells spacetime how to curve." This encapsulates the heart of general relativity. Spacetime is dynamic and responds to the presence of mass and energy. But Wheeler was also interested in the quantum nature of gravity. He proposed the idea of quantum foam, suggesting that at the Planck scale, the smallest scale of the universe, spacetime itself might be turbulent, fluctuating with quantum effects. These fluctuations could be revealed through the study of gravitational waves, potentially offering a window into the quantum nature of spacetime. At the quantum level, one of the most important principles to understand is the Heisenberg uncertainty principle, which states that there is a limit to how precisely we can know both the position and momentum of a particle at the same time. This principle is deeply connected to the idea of quantum fluctuations, where energy and matter fluctuate in unpredictable ways, even in a perfect vacuum. When we apply this idea to gravitational waves, the uncertainty principle suggests that measuring the waves themselves could be influenced by these quantum fluctuations. This means that detecting gravitational waves with absolute precision could reveal more than just the properties of distant cosmic events. It could also give us insight into the very fabric of spacetime, revealing how it behaves at the smallest quantum scale. Theorists have been exploring several frameworks to understand the quantum nature of gravity, and one of the most prominent is loop quantum gravity. Carlo Rovelli, one of the leading figures in this field, has proposed that space and time are not continuous, but instead composed of discrete quantized units. According to loop quantum gravity, spacetime is made up of tiny loops or networks of interconnected spins at the Planck scale. These discrete elements form the fabric of spacetime itself, and they might influence the behavior of gravitational waves. If loop quantum gravity is correct, the very nature of spacetime could change as gravitational waves propagate through it, offering a unique opportunity to test this theory through gravitational wave astronomy. Another important theory that seeks to reconcile quantum mechanics with general relativity is string theory, which proposes that the fundamental particles of the universe are not point-like objects, but rather tiny vibrating strings of energy. These strings vibrate at different frequencies, giving rise to different particles, and string theory suggests the existence of extraspatial dimensions beyond the three we experience in our daily lives. According to string theory, gravity is not just a force acting through space, but rather a manifestation of the interaction between these extra dimensions and the quantum strings that make up all matter. Lenny Susskind, one of the leading figures in string theory, has explored how string theory could explain the behavior of black holes and gravitational waves, suggesting that higher dimensional effects might influence the way gravitational waves propagate through spacetime. In the context of gravitational waves, string theory offers the intriguing possibility that extra dimensions could leave signatures in the waves themselves. As gravitational waves travel through spacetime, they might interact with these hidden dimensions, altering their properties in ways that could be detectable by future gravitational wave observatories. If this hypothesis is correct, gravitational waves could not only help us study black holes, neutron stars, and other cosmic phenomena, but also provide evidence for the existence of extra dimensions and the true nature of spacetime. As our understanding of quantum gravity and gravitational waves continues to evolve, we can also look forward to the future of quantum gravitational wave detectors. While LIGO and similar detectors have already made remarkable strides in detecting gravitational waves, they are still limited by the precision of their measurements. The next generation of detectors, such as the Laser Interferometer Space Antenna, LISA, will be even more sensitive, capable of detecting waves at much lower frequencies and from much farther distances. These new detectors could reveal new aspects of gravitational waves, including their quantum properties. In particular, quantum-enhanced sensors, which take advantage of the principles of quantum mechanics to improve the sensitivity of measurements, could help us study gravitational waves with unprecedented accuracy. This could open the door to new discoveries in both quantum gravity and the nature of spacetime itself. Gravitational waves, by their very nature, are a bridge between the quantum and classical realms. They provide a unique opportunity to study the structure of spacetime and test theories about the quantum nature of gravity. The more we learn about gravitational waves, the closer we come to resolving one of the greatest puzzles in physics. How do quantum mechanics and general relativity fit together? The future of quantum gravitational wave detectors holds the potential to unlock new insights into the deepest mysteries of the universe, helping us answer questions about the very fabric of space-time, the nature of black holes, and even the fundamental structure of reality itself. As our tools and theories continue to improve, the study of gravitational waves may one day reveal the quantum nature of space-time, helping us understand the universe at the most fundamental level. Whether through the lens of loop quantum gravity, string theory, or other frameworks, the detection of gravitational waves promises to be a key part of unlocking the secrets of the quantum world. The journey into quantum gravity is just beginning, and with each new discovery, we move closer to understanding the true nature of the universe. Gravitational waves offer us a remarkable opportunity to observe the very fabric of space-time itself. These ripples traveling across the universe are not just the result of distant cosmic events like black hole mergers or neutron star collisions. They are, in fact, a direct observation of how space-time behaves when mass and energy interact. In this way, gravitational waves serve as an invaluable tool for understanding the dynamic nature of space-time, as predicted by Einstein's general theory of relativity. When Einstein introduced his theory of general relativity in 1916, he proposed that gravity was not a force acting between objects in space, but rather a result of the curvature of space-time. This idea was a dramatic departure from the Newtonian view, in which gravity was simply an invisible force acting at a distance. According to Einstein, mass and energy bend the very fabric of space-time, and the curvature of space-time affects how objects move through it. The more massive an object, the greater the distortion it creates in space-time. In this framework, gravity is not a force that objects exert on each other, but a manifestation of the curvature of space-time itself. Gravitational waves are exactly what they sound like, waves that travel through space-time, stretching and compressing it as they pass. These waves are generated by extremely violent events, such as when two black holes collide or when neutron stars spiral into each other. As these massive objects accelerate, they disturb the fabric of space-time, sending out ripples that propagate outward at the speed of light. These ripples travel across the universe, carrying information about the events that caused them. One of the most remarkable aspects of gravitational waves is that they directly confirm a key aspect of general relativity, the dynamic nature of space-time. Space-time is not a static, unchanging backdrop on which events unfold. Instead, it is a living, breathing entity that responds to the presence of mass and energy. Just as a heavy ball placed on a rubber sheet will cause the sheet to warp and bend, so too does mass cause space-time to warp. Gravitational waves are the ripples in space-time caused by such distortions. They provide a tangible, direct way to observe the warping of space-time that general relativity predicted, offering a new window into the behavior of the universe. The relationship between gravitational waves and the curvature of space-time is one of the most profound aspects of this field. Einstein's equations describe how space-time is curved by the presence of mass and energy, and how this curvature dictates the motion of objects. Gravitational waves represent changes in this curvature, propagating outward as the mass and energy that cause them move through space-time. For example, when two black holes orbit each other and eventually collide, the intense gravitational interaction between them sends out ripples that carry information about the black holes, masses, spins, and the details of their collision. These ripples are incredibly faint by the time they reach Earth, which is why detecting them is such a remarkable achievement. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, is designed to measure these tiny distortions in space-time. The sensitivity of LIGO is astounding. It can detect changes in distance smaller than 1/1000th of the diameter of a proton, which is far smaller than anything we can see or measure with conventional instruments. Yet, despite their faintness, these waves carry invaluable information about the most extreme and distant objects in the universe. As we study gravitational waves, it becomes increasingly clear that space-time is far more dynamic than we once thought. General relativity describes how mass and energy curve space-time, but it also hints at the possibility that space-time itself is constantly shifting, reacting to the objects within it. Gravitational waves are a direct manifestation of this dynamic nature. They show us that space-time is not a static, passive stage. It is a malleable, active participant in the drama of the universe. But the study of gravitational waves is not just about confirming the principles of general relativity. It also offers the potential to unlock even deeper mysteries about the nature of space itself. As we continue to detect and analyze these waves, we may discover new insights about the fundamental structure of space-time. For instance, gravitational waves could help us probe the very early universe, moments after the Big Bang, when space-time was in its infancy and behaving in ways we can only theorize about. The signature of gravitational waves from the early universe could reveal crucial information about the conditions that existed before stars, galaxies, and even black holes formed. This could also provide a window into the nature of quantum gravity, a theory that seeks to reconcile general relativity with quantum mechanics. While general relativity works incredibly well on large scales, it struggles to explain phenomena at the smaller scales where quantum effects dominate. The quest for quantum gravity is one of the most challenging problems in physics today. The detection of gravitational waves might help bridge this gap, as the extreme conditions during black hole mergers and other cosmic events could provide a glimpse into how gravity behaves at the quantum level. If quantum gravitational effects are present, they could leave subtle traces in the gravitational wave signals we observe. Looking to the future, the potential for gravitational waves to unlock the deepest secrets of space is immense. As detectors like LIGO continue to improve in sensitivity, and as new observatories are launched, we will be able to study gravitational waves from even more distant and more extreme events. This could provide us with a much deeper understanding of space-time itself, its structure, its dynamics, and perhaps even its origins. Gravitational waves may eventually help answer questions about the nature of time, the structure of the early universe, and the fundamental workings of gravity at the quantum level. In addition to revealing the properties of space-time, gravitational waves could also offer new insights into the very fabric of the universe. For example, they could provide clues about the existence of hidden dimensions, as predicted by theories like string theory. If the universe has more than the familiar 3 spatial dimensions and 1 time dimension, gravitational waves might carry signatures of these extra dimensions, offering us a way to probe the deepest structure of reality. Detecting these signatures would be a groundbreaking discovery, expanding our understanding of the cosmos in ways we can only begin to imagine. Gravitational waves are not just a tool for observing distant cosmic events, they are a window into the very nature of space and time. As we continue to study these waves, we're not only confirming the predictions of general relativity, but also uncovering new aspects of the universe that we had never before imagined. The future of gravitational wave astronomy holds immense promise, and with each new discovery, we're drawn closer to understanding the true nature of space-time and the forces that shape our reality. Gravitational waves provide a powerful way to study the universe, but they also offer a glimpse into the ever-evolving nature of space-time itself. As we continue to observe and analyze these waves, we may unlock secrets about the cosmos that will reshape our understanding of space, time, and the very fabric of reality. The future of gravitational wave discovery is nothing short of thrilling. What we've witnessed so far is only the beginning of a new era in astronomy, one that will allow us to observe the universe in ways we never thought possible. As technology continues to evolve, the ability to detect and study gravitational waves will become more refined, allowing us to peer deeper into the cosmos and uncover phenomena that have previously been hidden from view. One of the most exciting advancements in gravitational wave research is the development of the Laser Interferometer Space Antenna, or LISA. Unlike LIGO, which operates on Earth, LISA is a space-based observatory designed to detect low-frequency gravitational waves. LISA will consist of 3 spacecraft orbiting the Sun in a triangular formation, separated by millions of kilometers. By measuring the tiny changes in distance between these spacecraft as gravitational waves pass through, LISA will be able to detect waves with frequencies far lower than those LIGO is capable of capturing. This will allow us to observe phenomena that are invisible to Earth-based detectors, such as the mergers of supermassive black holes in the centers of distant galaxies. LISA's sensitivity will open up entirely new areas of gravitational wave astronomy. For example, it could help us study the formation and evolution of supermassive black holes, which are thought to lie at the heart of every large galaxy. These black holes can have masses millions or even billions of times that of the Sun, and their mergers are expected to produce gravitational waves with frequencies much lower than those detected by LIGO. LISA will be able to detect these waves potentially allowing us to observe the formation and growth of black holes in the early universe, events that are currently beyond our reach. In addition to LISA, there are plans to continue upgrading existing detectors like LIGO. The upcoming advanced LIGO upgrades will increase its sensitivity, allowing it to detect more distant events and measure even smaller distortions in space-time. This will improve our ability to observe a broader range of phenomena, from the mergers of neutron stars to the collisions of black holes, helping to answer fundamental questions about the universe's most extreme objects. These upgrades are important because they will allow us to gather more data on events that happen in the far reaches of space and time. For example, by detecting gravitational waves from further and further away, we will be able to observe the universe as it was in its early stages, long before the first galaxies and stars formed. Gravitational waves from these early epochs could provide us with insights into the conditions of the universe during the Big Bang and reveal new details about the nature of spacetime itself. But beyond just observing distant cosmic events, gravitational waves have the potential to unlock some of the most intriguing mysteries of the universe. One of the most exciting possibilities is that gravitational waves could provide clues about dark matter. While dark matter makes up around 25% of the universe's mass, it has never been directly detected. Its presence is inferred by the gravitational effects it has on galaxies and galaxy clusters, but its true nature remains elusive. Some theories suggest that dark matter could be made up of exotic particles that might interact with gravitational waves in unique ways. If this is true, gravitational wave detectors like LIGO and LISA could provide the first direct evidence of dark matter. This would not only help us understand the elusive nature of dark matter, but could also lead to new insights into the fundamental forces of the universe. Gravitational waves could also reveal new information about the structure of space-time itself. For example, they could provide clues about the existence of extra dimensions, as predicted by string theory. According to string theory, the fundamental particles of the universe are not point-like objects, but rather tiny, vibrating strings of energy. These strings vibrate in more than the familiar 3 spatial dimensions, suggesting that the universe may have additional dimensions that are currently hidden from view. If these extra dimensions exist, they might influence the way gravitational waves propagate through space-time, leaving subtle signatures that could be detected by future observatories. The study of gravitational waves could thus offer a powerful tool for testing the validity of string theory and other theories of quantum gravity. Looking further into the future, one of the most exciting prospects for gravitational wave astronomy is the potential to study the very fabric of space-time itself. As we develop more advanced detectors and improve our ability to measure gravitational waves, we may be able to observe phenomena that have been completely hidden from view up until now. For example, we could eventually detect the gravitational waves produced by the merging of primordial black holes, which are thought to have formed in the early universe. These black holes could be much smaller than those we currently observe, and might provide insights into the very first stages of cosmic evolution. Moreover, gravitational wave astronomy could provide a unique way to probe the quantum nature of gravity. As we push the limits of sensitivity, we may begin to observe quantum gravitational effects, which could help us reconcile the worlds of quantum mechanics and general relativity. The search for quantum gravity, a theory that can explain both the extremely small scales of quantum mechanics and the large-scale behavior of space-time, remains one of the biggest challenges in physics. Gravitational waves might provide a direct link between the quantum and classical realms, helping us unlock the deepest secrets of the universe. The potential for gravitational wave astronomy is truly vast. As we continue to upgrade existing detectors and launch new missions like LISA, we will be able to observe an ever wider range of cosmic events, from the merging of black holes and neutron stars to the birth of the universe itself. Gravitational waves hold the key to unlocking new insights into the most fundamental questions in physics, questions about the nature of space, time, and gravity, and they will undoubtedly continue to shape our understanding of the cosmos for years to come. The future of gravitational wave discovery will depend not only on technological advances, but also on international collaboration. The success of LEGO and other observatories has shown the power of working together across borders to achieve something greater than any single country could accomplish alone. As we build more sensitive detectors and explore new frontiers in gravitational wave astronomy, continued collaboration among scientists, engineers, and institutions around the world will be essential. Only through this collective effort can we hope to unlock the deepest mysteries of the universe and understand the true nature of the cosmos. In the end, gravitational waves offer more than just a new way to observe the universe. They are a window into the fundamental workings of reality itself. With each new discovery, we move closer to answering the big questions about the nature of space, time, and the forces that govern our universe. The future of gravitational wave astronomy is bright, and the discoveries yet to come could reshape our understanding of everything from the formation of black holes to the structure of the universe itself. The discovery of gravitational waves has been nothing short of transformative for the field of astronomy. Before this groundbreaking detection, astronomers were limited to observing the universe through electromagnetic radiation, light, radio waves, X-rays, and so on. These methods have allowed us to uncover a great deal about the universe, but they are not without their limitations. There are many phenomena in the cosmos that are invisible to traditional telescopes, particularly those that involve extremely dense, energetic, or distant objects. This is where gravitational waves come in, offering an entirely new way to observe and understand the universe. Gravitational waves are ripples in space-time itself, created by the motion of massive objects, such as the collision of black holes or neutron stars. These waves propagate outward, carrying information about the objects that created them. The beauty of gravitational wave astronomy is that it provides a completely different perspective, one that isn't reliant on light or other forms of electromagnetic radiation. This new kind of listening allows us to observe the universe's most extreme and energetic events, offering insights into areas we've never been able to access before. One of the most significant impacts of gravitational wave detection is that it has opened a window to observe some of the most extreme phenomena in the universe. Events like the merger of two black holes, which was first observed by LIGO in 2015, were previously entirely invisible to traditional telescopes. These collisions release vast amounts of energy in the form of gravitational waves, and by studying these waves, we can learn about the masses, spins, and other properties of black holes, information that is otherwise hidden from us. The first detection of gravitational waves confirmed Einstein's century-old prediction and allowed us to observe black hole mergers in a completely new way, providing critical insights into the nature of these mysterious objects. But the potential of gravitational wave astronomy goes far beyond just black hole mergers. It also gives us a powerful tool for studying neutron stars, which are dense remnants of stars that have exploded in supernovae. When two neutron stars collide, the resulting gravitational wave signal is accompanied by an electromagnetic signal, known as a kilonova, which provides insight into the creation of heavy elements like gold and platinum. The detection of gravitational waves from a neutron star merger, such as the event GW170817 in 2017, confirmed that these mergers are responsible for producing some of the universe's heaviest elements, offering a critical piece of the puzzle for understanding stellar evolution and nucleosynthesis. The emergence of gravitational wave astronomy has also had a profound impact on how we study the evolution of stars and other massive objects. Stellar evolution, which describes how stars form, live, and die, has been studied for decades using electromagnetic observations. However, gravitational waves give us a new way to test existing models and theories. For example, the detection of gravitational waves from black hole and neutron star mergers allows us to test the properties of these objects, such as their masses, spins, and equations of state, which describe the behavior of matter under extreme conditions. This new data helps to confirm, refine, or challenge our understanding of how these objects form and evolve. By studying gravitational waves, we can also probe the interiors of objects that are otherwise hidden from view. For instance, neutron stars are so dense that their interiors cannot be observed using traditional methods. However, the gravitational waves emitted during a neutron star merger contain valuable information about the internal structure of the star. This has the potential to provide critical insights into the equation of state of ultra-dense matter, which is a key component in understanding how matter behaves in extreme environments. This is something that can't be measured using light or other electromagnetic radiation. As we move forward, the ability of gravitational wave astronomy to test and refine models of stellar evolution, black holes, and neutron stars will only expand. One of the exciting possibilities is that future gravitational wave detectors will allow us to observe even more distant and more energetic events, including mergers of black holes and neutron stars that occurred billions of years ago. These observations could provide a wealth of new data about the formation and evolution of the universe itself, including the early stages of cosmic history when the first stars and galaxies formed. Gravitational waves also offer the possibility of discovering entirely new phenomena, further expanding the horizons of astrophysics. For example, the detection of gravitational waves from the early universe could provide insights into the conditions that existed shortly after the Big Bang, offering a unique opportunity to study the universe during its infancy. These waves could carry information about the very beginning of time, potentially revealing new details about the origins of the universe and the fundamental forces that shaped its evolution. But gravitational wave astronomy is not just about studying familiar objects like black holes and neutron stars. It also offers a way to probe new and exotic phenomena such as the potential presence of dark matter. Dark matter makes up about 25% of the universe's mass, yet it remains invisible to traditional telescopes. Its existence is inferred based on its gravitational effects on visible matter, but it has never been directly detected. Some theorists believe that gravitational waves could provide clues about the nature of dark matter. If dark matter is composed of exotic particles, these particles might interact with gravitational waves in ways that leave detectable signatures. The detection of these signatures would not only help us understand dark matter, but could also provide new insights into the fundamental forces of the universe. The future of gravitational wave astronomy is incredibly exciting, and we are only beginning to scratch the surface of what these waves can teach us about the universe. As gravitational wave detectors continue to improve in sensitivity and new missions are launched, we will be able to observe even more distant and extreme events. One of the key goals for the future is the detection of lower frequency gravitational waves, which could be observed using space-based detectors like the Laser Interferometer Space Antenna, LISA. LISA will be able to detect gravitational waves from sources such as the mergers of supermassive black holes, which are thought to be common in the centers of galaxies. These waves could provide us with valuable insights into the formation and growth of these massive objects, as well as their role in the evolution of galaxies and the universe. In addition to expanding our understanding of black holes, neutron stars, and dark matter, gravitational wave astronomy has the potential to help us answer some of the most fundamental questions about the nature of space-time itself. By studying how gravitational waves interact with the fabric of space-time, we could learn more about the fundamental structure of the universe, and perhaps even uncover hidden dimensions or other aspects of reality that we can't yet imagine. Gravitational waves provide a direct window into the workings of space-time, and as we continue to detect and analyze these waves, we will inevitably uncover new insights into the deepest mysteries of the cosmos. In conclusion, gravitational wave discovery has revolutionized the field of astronomy, opening up new avenues for exploration and offering profound insights into some of the most extreme and distant phenomena in the universe. As our detection capabilities continue to improve, gravitational wave astronomy will undoubtedly expand the horizons of astrophysics, providing us with answers to long-standing questions and uncovering new phenomena that will shape our understanding of the universe for years to come. The future is bright, and the discoveries ahead promise to be as exciting and transformative as those that have already been made. The discovery of gravitational waves in 2015 was a moment of immense significance, not just for the scientific community, but for the world at large. It marked the first time we could directly observe the ripples in space-time caused by some of the most violent events in the universe, like the collision of black holes. This discovery not only validated Einstein's theory of general relativity, but also opened up a whole new field of study, gravitational wave astronomy. But beyond the scientific implications, the public response to this discovery was equally transformative, sparking a renewed sense of curiosity and wonder about the cosmos. Before the detection of gravitational waves, space exploration was largely dominated by visual data. Images from telescopes, photographs of distant galaxies, and spectacular views of space from rovers and satellites. While these images were awe-inspiring and offered profound insights into the universe, they were still bound by our senses and our limitations in observation. Gravitational waves, on the other hand, introduced a new way of listening to the universe. These invisible waves, generated by cosmic events like the merging of black holes, offered a completely new form of detection. The discovery allowed the public to experience space in a way they hadn't before, by hearing the very fabric of space-time itself ripple in response to cosmic events. For many, the detection of gravitational waves transformed the way they thought about the universe. No longer was space just something vast and distant, something we could only observe from a distance. It became something we could feel and hear, something dynamic and alive, constantly shifting and responding to the movements of celestial bodies. This shift in perception has inspired a greater public interest in space and science. Gravitational waves have not only given us a new way to observe the universe, but they have also helped to bridge the gap between complex scientific theories and the general public, showing that even the most abstract ideas in physics have a real-world observable impact. The role of media in shaping the public's understanding of gravitational waves cannot be overstated. When LIGO made its first detection in September of 2015, the news spread quickly, garnering widespread media coverage. Major news outlets, from newspapers to television stations, provided extensive coverage of the discovery, explaining the significance of the event to audiences around the world. The coverage often framed the detection as a monumental achievement not only for physics but also for humanity's quest to understand the universe. This media attention sparked widespread curiosity and excitement, drawing people who might not have previously been interested in physics or astronomy into the world of gravitational waves. Scientific outreach efforts played a critical role in making this complex discovery accessible to a broader audience. Organizations like LIGO and other research institutes worked hard to explain the science behind gravitational waves in simple, engaging terms. Their efforts included public talks, educational videos, and interactive websites that helped demystify the science for people of all ages. The fact that such an abstract concept as gravitational waves could be explained in a way that was understandable and exciting to the general public helped shift the conversation about science from something distant and esoteric to something people could relate to and care about. For many, the detection of gravitational waves ignited a spark of curiosity. The idea that we could hear the universe through these invisible ripples captured the imagination of the public, inspiring many to dive deeper into the world of science. Schools, museums, and universities used the discovery as an opportunity to engage students and the general public with the wonders of physics and space exploration. For students, the idea that a career in science could lead to groundbreaking discoveries like this became not just a possibility, but an inspiring reality. In a sense, the discovery of gravitational waves reminded us all that there is so much more to learn about the universe, and that curiosity, no matter how small or big, can lead to something truly transformative. This excitement wasn't confined to just the discovery itself. The implications of gravitational wave astronomy stretch far beyond what we know today. While the detection of gravitational waves from black hole mergers and neutron-star collisions was groundbreaking, it's only the beginning. As gravitational wave detectors like LIGO continue to improve, and new observatories like the Laser Interferometer Space Antenna, LISA, prepare for launch, the field will only expand. These advancements will allow scientists to explore even more distant and faint gravitational waves, possibly revealing entirely new phenomena that we've never even imagined. In particular, the potential to observe gravitational waves from the early universe is one of the most exciting frontiers in gravitational wave astronomy. These waves could reveal insights into the conditions that existed moments after the Big Bang, information that would provide a clearer picture of the universe's birth and its earliest evolution. The detection of these waves could help answer questions about the nature of space-time itself, about the fundamental forces of the universe, and about the very origins of everything we know. This next chapter in gravitational wave astronomy has the potential to inspire a new generation of scientists and science enthusiasts. As more discoveries are made and new tools are developed to explore the universe in this way, the possibilities for future breakthroughs are endless. And just as the discovery of gravitational waves sparked a wave of curiosity about the cosmos, future discoveries may inspire a whole new generation to become explorers of the universe, whether through research, education, or simply a passionate love for science. The importance of this curiosity and the role of discovery in shaping our perception of the universe cannot be understated. Gravitational wave astronomy is far more than just a scientific pursuit. It's a reminder of the importance of exploration, of asking big questions and seeking answers in ways we never thought possible. As we continue to listen to the universe through gravitational waves, we're not only expanding the horizons of astrophysics but also expanding our own horizons as a species. We are reminded that the universe is vast, mysterious, and filled with wonders waiting to be discovered, and that our curiosity, fueled by science, will lead us to uncover more of these mysteries, one wave at a time. In many ways, gravitational waves have transformed the way we see the universe. They've shown us that space is not an empty void, but a dynamic, ever-changing field. And as we continue to make discoveries, the potential for what lies ahead is limitless. The world of gravitational wave astronomy is just getting started, and the possibilities for future discoveries are as vast as the cosmos itself. The discovery of gravitational waves is a monumental step forward in our understanding of the universe. Not only does it validate some of the most fundamental principles of Einstein's general relativity, but it also opens up a new frontier in physics that could lead to answers for some of the deepest questions we face about the nature of space-time, gravity, and the fundamental forces of the universe. As we continue to study gravitational waves, we are not simply observing the after-effects of cosmic events. We are testing the very limits of our understanding of physics itself, with the potential to uncover a unified theory that could tie together the disparate forces of nature in a theory of everything. At its core, the detection of gravitational waves is a profound validation of Einstein's general theory of relativity. For over a century, general relativity has been the best framework we have for understanding the force of gravity. It describes how mass and energy curve space-time, and how that curvature dictates the motion of objects. In the case of gravitational waves, these distortions in space-time travel outward from their source, just as Einstein predicted. The fact that we can now detect these waves with precision proves that general relativity is correct, at least in the context we've observed so far. But there are still many questions that remain, especially when we look to the smaller scales of the universe, where general relativity and quantum mechanics, the two pillars of modern physics, do not yet mesh. The search for a unified theory, one that merges the laws of gravity with the laws of quantum mechanics, is one of the greatest challenges in physics. Currently, general relativity describes large-scale phenomena, everything from the motion of planets to the behavior of black holes, while quantum mechanics governs the behavior of particles on the smallest scales, like atoms and subatomic particles. These two theories are incredibly successful within their own realms, but they are fundamentally incompatible. Quantum mechanics works in the world of the very small, but when we try to apply it to gravitational forces, especially around black holes or in the early universe, we run into major problems. General relativity, on the other hand, works on the grand scale but doesn't account for the quantum world. This is where gravitational wave astronomy could play a pivotal role. Gravitational waves provide a unique opportunity to probe the limits of general relativity, testing its validity under extreme conditions. They give us a direct, observable signal that can reveal how space-time behaves in the presence of incredibly massive and energetic objects. Gravitational wave detections, like the merger of black holes or neutron stars, offer us glimpses into the behavior of space-time in ways that were previously beyond our reach. These cosmic events, which are often billions of light-years away, send ripples across space-time that we can measure with extraordinary precision. As we observe more and more gravitational waves, we may begin to see signs of something that cannot be explained by general relativity alone. For example, we might detect subtle distortions in the waves that could be indicative of quantum effects in the behavior of space-time itself. If the fabric of space-time is quantized, as some theories suggest, gravitational waves could provide evidence of these quantum properties. This would mark a significant step toward the unification of general relativity and quantum mechanics, and potentially reveal a new theory of gravity that incorporates both quantum principles and the curvature of space-time. One of the leading frameworks for achieving this unification is loop quantum gravity. This theory proposes that space-time is not smooth and continuous, as general relativity suggests, but instead consists of discrete chunks, or loops. The idea is that space-time itself is made up of small, indivisible units at the smallest scales, and gravitational waves could reveal these discrete properties. If loop quantum gravity is correct, then gravitational waves could carry signatures of these tiny, fundamental units of space-time. Detecting these signatures would help confirm the existence of quantum gravity and provide valuable insight into how gravity works at the smallest scales. Another promising approach is string theory, which posits that the fundamental particles of the universe are not point-like objects, but rather tiny, vibrating strings of energy. String theory suggests that gravity, along with the other forces of nature, arises from the interactions of these strings. In this framework, gravity is not a force that exists within space-time, but rather a manifestation of the interactions of these fundamental strings in a higher dimensional space. If string theory is correct, gravitational waves could reveal the presence of extra dimensions or offer clues about the behavior of strings at the Planck scale, where quantum gravity effects are most prominent. The connection between gravitational waves and quantum gravity also raises intriguing possibilities for testing some of the more speculative aspects of theoretical physics. For example, some theories suggest that gravitational waves could carry information about the very early universe, just moments after the Big Bang. In this era, space-time was far more turbulent and chaotic, and the properties of gravity may have been vastly different from what we observe today. Gravitational waves from this early period could provide crucial information about the conditions that existed during the first fractions of a second of the universe's existence. This could shed light on the mysteries of cosmic inflation, the rapid expansion of the universe shortly after the Big Bang, and offer insight into the origins of both space and time. By studying these waves, we might also begin to probe the fundamental fabric of space-time itself. Gravitational waves are sensitive to the curvature and structure of space-time, and by analysing their properties, we could learn more about how space-time behaves in extreme conditions. This could lead to new discoveries about the nature of black holes, the geometry of space-time, and even the possibility of higher dimensional spaces. Gravitational wave astronomy, in this sense, offers a potential window into a deeper, more fundamental level of reality, one that could unite the disparate forces of nature in a unified theory. Ultimately, gravitational wave research holds the key to answering one of the most profound questions in physics. How can we reconcile the strange and mysterious world of quantum mechanics with the large-scale, smooth curves of space-time described by general relativity? As our detectors improve and we observe more gravitational waves, we will continue to test the limits of both theories. These waves, which provide a tangible, measurable signal, offer us a rare chance to probe the most fundamental aspects of gravity and space-time. In the years to come, the study of gravitational waves will likely play a critical role in unraveling the deepest mysteries of the universe. It may be through these waves that we finally uncover the long-sought theory of everything, a unified framework that can explain all of the fundamental forces of nature. As we continue to push the boundaries of our understanding, gravitational wave astronomy may not only reveal the true nature of gravity, but also offer insight into the very structure of reality itself. It is an exciting time in physics, and gravitational waves are leading the way to new discoveries that could change everything. Gravitational wave astronomy represents one of the most profound advancements in our understanding of the universe. This field has opened a new window into observing the cosmos, allowing us to detect and study the ripples in space-time caused by some of the most violent and energetic events, such as black hole mergers and neutron star collisions. These waves, invisible to the naked eye, have provided a fresh perspective on the universe, revealing hidden aspects of the cosmos that traditional telescopes could never uncover. With each new discovery, we are not only confirming long-standing theories, but also challenging our fundamental understanding of gravity, space-time, and the very nature of reality itself. The importance of gravitational wave astronomy goes beyond just observing these waves. It is about the potential to reshape our entire framework of physics. From the validation of Einstein's general theory of relativity to the exploration of quantum gravity, gravitational waves serve as a bridge between the known and the unknown. They allow us to probe the fabric of space-time in ways that were previously unimaginable, providing insights into phenomena like black holes, neutron stars, and possibly even the very beginning of the universe itself. This groundbreaking field owes much to the brilliant minds that have paved the way. Albert Einstein's general theory of relativity provided the theoretical foundation for the existence of gravitational waves, predicting that massive objects moving through space-time would create ripples. Kip Thorne, a leading figure in gravitational wave physics, helped shape the understanding of these waves and their potential detectability. Alongside him, Rainer Rice, Barry Barish, and the team behind LIGO's construction and operation made the first direct detection of gravitational waves possible in 2015, confirming Einstein's century-old prediction. But it's not just the well-known figures who have contributed to this extraordinary achievement. Scientists like John Wheeler, Carlo Rovelli, Lenny Susskind, and Jocelyn Bell Burnell have all played critical roles in shaping the ideas that have led us here, offering insights into everything from the nature of black holes to the possible quantum nature of spacetime. The journey of gravitational wave astronomy is only beginning. With the launch of future observatories like the Laser Interferometer Space Antenna, LISA, and the continued upgrades to detectors like LIGO, we are poised to make even more exciting discoveries. As our ability to detect and study gravitational waves improves, we will be able to observe more distant and faint cosmic events, potentially uncovering new phenomena that could transform our understanding of the universe. Whether it's the search for evidence of dark matter, exploring the quantum properties of gravity, or investigating the conditions of the early universe, gravitational waves promise to open doors to new frontiers in astrophysics and fundamental physics. In the end, the study of gravitational waves is not just about uncovering the mysteries of distant galaxies or understanding the most extreme objects in the universe. It's about the quest to understand the very fabric of reality. As we continue to listen to the universe through these cosmic ripples, we're uncovering a universe far more strange, intricate, and interconnected than we ever imagined. The future of gravitational wave astronomy holds the potential to reveal a deeper understanding of the cosmos, from the smallest quantum particles to the vast, ever-expanding universe and our place within it.